Music theory with OneNote. Hertz versus hue, mapping to a circle. In other words, we're going to measure pitch in hertz, but it's not going to actually hurt. That's just the measurement tool. It doesn't hurt. We're going to measure it within hertz, however, which results in a spectrum, which is kind of like a number line going linearly, infinitely upwards, which we will then bend into a circle with 360 degrees, followed by doing the same thing to color or hue, which we can measure with the length of the wavelength, resulting once again in a spectrum going linearly, infinitely upward, which we could also bend into a circle with 360 degrees, allowing us to map the color wheel circle directly on the pitch wheel circle. Then we'll want to pop that circle off the page with a 3D component. So get ready and some coffee, because although we're just playing with OneNote, it's a beautiful note. You're not required to, but if you have access to it and would like to follow along, we're currently in the OneNote file of Modal Node System MNS Presentation 2003 OneNote Hertz versus hue mapping to a circle presentation list, which we plan on adding plenty more to shortly. Also noting, in this OneNote presentation, we'll spend all of our time on the music theory side of things, but we have another similarly numbered and named presentation where we actually build these tables in Excel, practicing music, Excel, and just table visualization skills at the same time. Reminder of our overall objective, because sometimes we can get kind of lost in the weeds here. We want to make a practical tool utilizing color in the most efficient way to better understand music theory in general and better navigate the fretboard in particular. This being an example of a fretboard where we have the low or heavy E string on top. I know it is very colorful, but we can often tone down the color when using this in practice by, instead of coloring all 7 notes within the collection of notes we're working in, we just color the notes that we're really focused in on at the time. So what we're doing is mapping the color wheel directly onto the pitch wheel. That's going to result in absolute colors that we can associate with each of the 12 pitches, and later we'll actually get into colors that we can blend together when we play 2 notes at the same time, which is basically you can think of as an average or a log average if you want to put it on the circle. We'll get into that basically later. But for now, we have one color for each of the 12 notes in the musical alphabet. Or we can use a color set that doesn't tie out to the notes, but rather to the modes. And why would we want to do that? Well, I think if we can associate the color to each of the notes, many people will be able to have more neurons firing in the head. And that, in my theory, is what we want to do to optimize the use of the fretboard, which, by the way, is a little bit controversial or counterintuitive, because you might think, hey, look, I only want to learn things one way. I want to specialize my brain to learning it with just the letters, for example. Why are you putting numbers here? Why are you putting dots here? Why are you putting the modal number system here and the letter modes and now colors and then formulas and so on and so forth? I'd rather just spend all my time learning it one particular way, and then I'll get really, really good at seeing it that way. And that's kind of the mistake a lot of people, including me, made. I believe it's a mistake in like math class, for example, right? You're going to say, hey, look, all these other ways that people are teaching me, I know how to do it my way. But what you want to do is see how to do it your way that leads you into seeing what they're talking about from their perspective so that you can branch out. Meaning, the whole goal of almost life in general, I feel like, is to look at actual connections between different things, and that actually makes you understand the thing that you're focusing in on better. You can hyper specialize, which can actually cause a problem because you're not getting the cross-pollination of the neurons. You're not seeing the connections. Doesn't mean you want to connect everything. Then you'll start doing conspiracy theories, right? It has to be a legitimate connection, right? But my theory is, the more different ways we can visualize the same thing, then the better we understand that same thing. You're going to go further than trying to specialize and understand it one way, and just focus all your time on that one particular narrow focus. Okay, and again, that might be controversial like an academia standpoint where that's kind of what happens. Right? You have to focus, so there's kind of some balance in it. Anyway, so we have the system that is going to be starting out. This top one up here is around the collection of notes around the C major, And then we have the letter name, the number name, if we number 1 through 12 for the note. And then we have the Nashville number system number, which is basically an absolute modal system number, which is what the letter is: Mixolydian, Locrian, Ionian, Aeolian. And then we have the dots and the squares, which are filled in or not filled in, which is another way to just visualize the pattern, which I think, I wish I remember who I saw that from. I think it's a really good idea, that it's basically the same thing as if you number it, looking at the pattern as even and odds, which is kind of like a computer looks at things, right? It's got on, off, 1 or 2, right? 2 options. It's either a circle or a dot. It's filled in or it's not filled in. It's even or it's odd. So if I look through the pattern, square, 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 circle, 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 that's the whole, whole, half, whole, 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 half kind of pattern. Anyways, so this one gives you all of the colors here tied to an absolute system for the notes. And so you can see this one, if I move it up, this A is the same, even though down here we're in the key of 7-note collection around the D major. We have the same absolute notes that are colored. Now that's great, but it's kind of similar to trying to memorize all of the notes instead of memorizing the continents, which I still think there's value to do, because then you have a better association, a different association between a number system, a letter system, and a color system, to just memorize the 12 notes. But oftentimes we're going to want to follow the pattern as we go through the 12 collections of 7 notes. So for that, we would want to instead, here's the same color system we started with, but instead of tying the color to the note, we're going to tie it to the mode, the Ionian mode. So here's our position 1. And if then I move it up to the collection of notes around the D, the whole thing moves up. So now the whole thing moved up here, and we have the same color system. This green no longer ties out to the mapping of the color wheel that is going to be the similar thing of having Hertz versus hue, but it does give you the same color system, kind of pulling from or using the key of the major scale, the 7-note collection around the C major, as we often do as our key, our reference point. All right, so that's a really practical tool that we'll get into how to use it later. Now we're getting into kind of understanding how we're going to build that, why we come up with the colors we're going to come up with, and so on. So we took the Hertz wheel, we're going to recreate the system in using modern technology rather than trying to go back to ratios like Pythagoras or whatever, right? Because now we have the measurement in Hertz. So we measured this thing out in Hertz, and then we said, hey, look, if I measure it in Hertz, we have this doubling thing, meaning it goes from 440 to 880. We start at 440, which is an A, which is the middle part of the piano. They call middle C the starting point, but really the letters from 440, A to G sharp, are really what I would like to say that's the middle part of the piano, right? That's the middle part that we play on the guitar as well. And we know that if it double it to 880, meaning the number of waves that oscillate within a time frame, I think it's a second, doubles, then we hear a unison. It repeats. That means we have to squeeze the pitches in between these two numbers somehow. So the first way you would think to do that, if you picked 12 notes, is just to have an equal spacing. So you just take the 440 positions, 440 to 880 has 441 points if you count it wave by wave, one oscillation up by one oscillation up. But if you do that, then you get this problem that it doesn't double properly. So it fits, you can get it to fit, but it doesn't double properly, and we need it to double properly so that the octaves work. Otherwise, it won't work. So what do? We do this kind of logarithmic thing, meaning I think about it this way. I want to take these 440 units over here and squish it into 360 so that I have a circle that I can make it into a circle. So this needs to be 360 to make it into a circle. So how do we do that? We use our log average formula to bend this into a circle. And we talked about that last time, but that in essence gives us 360 measurements over here. I want all 360 measurements because later we're going to talk about intervals. And so I don't want just the 12 notes. I want all 360 because if you bend a string, or if you play 2 strings or 3 strings a chord, you can represent that by like an average possibly of all the hertz, or log average that would remain on the circle. So we'll talk about that later. So I want 360 to give me more detail so we can do more stuff beyond just the 12 notes. So then we can also do that for the octave up. So we could do that for the octave up, which would be like a spiral staircase system. We'll get into that more later. But now we want to do the same thing with color. So color has a similar phenomenon. Now it's not exactly the same. I've listened to people online that have really cool ideas. I like borrowed that, or which is a nice way of stealing, I guess, the idea of the circles and the dots representing like even and odd numbers and whatnot. So I think there's some really good intuitions out there, but I think also there's some misconceptions that people are saying that the color is like the same thing, like almost like we're taking in the same kind of information in our ears as our eyes, and you can measure it. The measurements would map 1-to-1, which I don't believe is exactly right? We can measure color. We measure pitch by the oscillations. We can measure color by the length of the wavelength. But it doesn't have this circular pattern. It doesn't repeat. Color doesn't repeat. So you might say, well, why do we have a color wheel then? I've seen a color wheel. That's true, but that's kind of because we kind of forced it into a circle, and we forced it into a circle kind of what we did with the sound, but they actually fudged it a little bit as well. So they kind of made the end of the circle tie back into the beginning by forcing it to go back to red. That's where it goes from magenta back to red. So we'll talk about that more later. But right now and it also doesn't have the second octave. So what can we do then? We can use that idea to bend the color into a circle and then map it onto directly our middle area, like the middle octave that we just put together. But it's not going to easily fit onto the pitches as we go up an octave and down an octave, because the color doesn't act that way. All right, so it's similar. It's a beautiful analogy. We should totally use it. The fact that we're not doing this to teach both color and pitch in grade school is crazy. Like, we should be doing this like in grade school. This is how we should learn color and pitch, comparing and contrasting them, and math and fractions, right? All of this should be done in grade school to me. If the fact that it's not is like, I don't know, I'm shocked that they haven't done. Okay. So that's going to be, so we're going to take our wavelengths. So the wavelengths are measured, I believe, in nanometers. So all we're doing is now we're looking at the length of light, which again, I have a tough time visualizing how exactly you measure that, but they could do it apparently. So I'm going to say, okay, I'll accept that. They're measuring the length of light, right? And so if you measure the length of light, then there's a spectrum of the light that we can basically see. So that's what we want to map on. If the light is outside of our visible spectrum, it's not going to help us with our color wheel, because I'm not going to map it onto the pitch, because I won't be able to see it, right? So this is something you can ask ChatGPT, or this is how I would use my AI tools. I would say, hey, look, what's the range of color measured in nanometers, or possibly what do they even measure it in if we don't know that, right? What's the range of color? And they're going to give you a range starting at like 380, and then it goes up to something like 700 or something like 750. Now the problem is, some people are better at perceiving color, particularly at the top end of the range. So it's not like it stops suddenly, but we want color that we can see pretty clearly. Everybody can see it. So that seems to be closer to 700. So you might be now saying, hey, look, you're fudging the numbers. You're just picking numbers randomly. Yeah, we have to have some kind of cutoff, right? It's a little bit of an analogy. So we're going to have some kind of cutoff. It starts at like 380 that we can measure it, ends at like 700. You can see it's a spectrum, which almost is a political word in the United States. It's like, are you calling it gay? And it's like, I'm not calling, or LGBT, are you calling? No, I'm not. I'm saying that just means it's linear. I'm just saying it's linear, okay? It goes up in a linear way, almost like you can imagine like in a number line to infinity, because we're measuring, the length of the light, right, is going to be the idea. So it's a linear progression going up is the idea. So what if we're going to bend it into a color wheel? We're going to have to do the same thing we did with the pitch, right? We're gonna have to bend it. We're gonna have to bend it around, and we're gonna have to fudge it a little bit because the end of the spectrum doesn't really tie back into the start of the spectrum from our perspective of color, right? We want the red to tie back in, so we're gonna add, like, I think magenta is what we add. So anyway, so if we went one by one, we'd have 380, 381, 382, 383, and so on and so forth. I'm just adding 1 nanometer up. So we're going one of our measurement tools by one. It would be like going inch by inch up. And we end up with, and how many, if I start at 380 and I go up to like 700, which is the spectrum, I end up with 321 nanometer intervals differences, right? So that doesn't tie out to 360, which is what we would need to properly bend it into a circle, right? So this one is actually below 360. So on the pitch wheel, I had to compress it to 360. This time we're gonna have to expand it to 360. I wanna have 360 degrees to make it into a circle. That's the log thing that we do, right? So if I don't do that and I just take 321 and divide it by 12, that would be our equal spacing. We're gonna get an uneven distance, right, of 2675. So if I try to make my 12 colors to map onto my 12 notes, then I'm gonna end up with a problem, right? Because it's not gonna rotate around properly again. Like if I could go up and make a 3D component, it wouldn't work, even though color doesn't have the 3D component, but we want to map it on conceptually to the pitch, which does have a 3D or doubling component as we go up. So we'd end up, if we did the same thing, what you would first think to do would be equal spacing. So it would be 27. So I'd start at 0, then up 27. So I'd look for like around 27. I rounded it. That would be 406. So you would think we would have a 406 color wavelength, which would be whatever color that is. It starts at red, and then it goes up, it goes up around the color wheel from red. And we'll look at this. We'll look at the spectrum more later, but that's going to be the idea. Here's just a rough idea of it. So here's the spectrum of 360 degrees that we're gonna bend it into 360. But the idea is it starts at red, right? And then it goes up to yellow, and then green, and then it goes into this blue, and then like purple, and then that's kind of where it stops. Like I believe the linear progression, the spectrum. Don't get political. It's the spectrum. Don't get, but I think it stops right there, and then they fudge it, right? Because we don't want it, because purple doesn't tie back into red as easy, right? So that's when they get into magenta. So magenta isn't actually measured in, I don't believe that's actually a wavelength color. So it's not like as the length of the wavelength goes up, it's not like you get to like magenta. They kind of fudged it to magenta because then they want it to bleed back into the red. So they bent it in. So this system bent it into a circle and then fudged it, which actually works perfect for us because that's the perfect analogy. So they've already kind of done that, but I want to recreate it just so we can basically get an idea of what it's doing. And if we work in something like Excel, we have to convert it from this 360 degree thing, which is an HLS or something color system, to the color system in Excel. And Excel uses this numbering color system, which is they call it hex. And they use this numbering system, which takes into account not just the hue, which is what we're measuring here, but also the other factors like lightness and brightness. So I know this gets a little wonky here, but just the idea here is we're measuring hue, which is basically the color itself, not getting into brightness and lightness. We're just measuring one dimension of color, which is determined by the length of the wavelength. Okay, once we have that, then I would like to choose the brightness and lightness that pops the best, which is a lightness of like 0.5. We'll talk about that later. And then I can add the added dimension of 3D by choosing a different lightness or brightness as we go an octave up or an octave down. But that's just an analogy. Why? Because the phenomenon doesn't actually include lightness and brightness. It's a different thing. Meaning with pitch, it repeats, the circle happens, you get an octave up as you increase the number of oscillations, the wavelengths per second. It just happens naturally. But with color, it doesn't, because we're only looking at hue when we measure the length of the wavelength. We're not measuring, I don't believe, lightness or brightness. Those are other things that we can add to it after. They're measured differently. So after I figure out the right hue, then we can say, do I want to make it lighter or brighter, which is closer to white light or closer to black, right? So we'll talk. So it's a different measurement that we can use, but it doesn't. The phenomenon doesn't happen the same as it does in sound. Okay. So that this would be the equal spacing. But we don't want to do equal spacing. We want to do the logarithmic spacing. So we're going to say now, what I want to do is make it into a circle. So I'm going to expand these units, which there's only 321, to 360. So I want it to fit on 360-degree circle. I'm going to start at the same starting point of 380, and then I'm going to draw a circle. So you can imagine that that's the starting point of the circle, and then I'm going to put a compass that's the radius down here, right? The compass point goes here to draw a circle, and then I draw a circle around that point that has 360 degrees. With this formula, it's going to be that starting point of 380 times 2, because we're mirroring the doubling capacity that happens when you double it for the pitch, and then to the power of the degree, which we're going to start at 0, 1, 2, 3, and so on, divided by the number of degrees in a circle, 360. And we end up now with 360 equally spaced units that would map onto a circle. So that's great. So that's what we call the logarithmic spacing. Now I just want 12 of these numbers. I like to have all the numbers, 360, but because I want to be able to play with things like bending a note that's not going to land on one of the 12 notes that we look at. So I'd like to have and octaves and chords, which can be thought of as log average or an average. So I want the 360, but now that we have them 360 units, I can now take equal spacing of 360, which will give me the logarithmic spacing, 360 divided by 12, at least an average of it, good enough for our purposes. So we want the 12 notes. These are going to be the note names now: A sharp or B flat, B, C sharp or D flat, D sharp or E flat, E, F sharp or G flat, G, and then G sharp or A flat. So then we're going to say it starts at 0 and then it goes up to 30. So 0 is 380, 30. If I go up 30, that's going to be a 403, right? And then if I keep on going down, that's going to give us these sets of colors. Now, these sets of colors, then, you can say, how could I convert these sets of colors to actual color? Well, you could ask ChatGTP. You can say, hey, look, these are the colors that I want measured in nanometers, and I want you to give me ChatGTP or whatever system you want to use for AI system. I want you to give it to me in hex numbers. So you could do that, right? That would be a conversion, and that would be the best analogy from color to pitch from a mathematical standpoint. However, we're going to use the HLS system, which in essence has already done this, meaning this color that we mapped out here, these are the HEX numbers, but we mapped it out from a 360 system, which is an HLS measuring system. The reason it's not going to tie into exactly what we derived here from a nanometer standpoint is because they fudged it, right? If we mapped it into a circle, the circle would have 360 degrees that I believe would stop somewhere around here, this color, which is a shock. It's too jarring from a circle standpoint to go from this color back to red. See, it would just be like ending. Your circle would have a tail, the tail end of the circle, the 12 on a clock, or the 11 on the clock is going to look drastically different than the 1. We don't want that. We want it to blend. So that's why they made up magenta here to blend it back into red. So this red at the bottom of the spectrum is not natural to the spectrum. It's not part of the length of the light. They fudged it from accounting terms. This is a technical accounting term. They put the plug in. They fudged it. They made it reconcile. They made it balanced. They plugged it, right, with the red. And so but it works perfect for what we want. So what we're going to do is we're going to say, okay, I see what they did here. So we're just going to imagine that this 360 degrees, I'm going to kind of drop the nanometers. I don't really care about the nanometers anymore. That's just that we just showed that to see how to get there. What I care about now is the 360 degrees give me the HLS, which is the color wheel in hue. The color wheel in hue doesn't have the lightness or brightness, I don't believe, or you're going to set it at like 0.5. So now we can ask ChatGTP, which is what I kind of did here, and said, ChatGTP, give me the 360 degree color wheel, but give me the HEX, the hex number, which is the Excel number. And you can even ask it, give me an Excel worksheet that maps out the 360 degrees from the HLS system, but convert it to hex and format the color in the cell so that you can actually have in Excel all of the colors mapped out for the 360 numbered system, and you have the conversion number and the actual formatting of the color. Now, what it can't do, that I would like it to say, give me conditional formatting for all of it, right? ChatGTP isn't that sophisticated yet. I'd like it to give me conditional formatting for all 360 degree colors, that if it has this symbol in it, then you're going to give me each color or something. I can't get ChatGTP to do that, but the fact that it could do this is super cool. Now these numbers here, so that means I don't have to do the conversion. You could double check the conversion also by doing an HLS to HEX conversion. To do that, we want to maximize the brightness of the color. So usually that would be a lightness of 0.5, I believe. 0.5 lightness will give us and the problem here is that this HEX number takes into consideration not just hue, but also lightness and brightness. And I think it's derived from the way our eyeballs work more with mixing together 3 prime colors and so on. So it's derived a little bit different. So these numbers don't make any sense from a 360. You can think of it just like a massive table that's going to basically have the hue as well as the brightness as well as the pitch. So we have to convert the 360 in our circle degree, which we already have a reference to, HLS, I believe is the name, and then just ask ChatGTP to convert it using this, or just have this in Excel. This would be 360 degrees and these would be the numbers, and then we could just convert it. So that's that's the tool that we'll use going forward. Now again, you might say that's a little tedious. You don't need all that because you just need 12 of them, right? So here's the HEXs for all 12, which again, I could just ask ChatGTP, hey, look, these are the HLS unit. Wait, these are actually not the actual HLS. These are them, right? These are the 360 units, and just ask ChatGTP, convert these HLS and these to this for 12. And then again, ChatGTP will give me the number that I can reference in Excel to pull it over, which is great. And then I can use conditional formatting in Excel or whatever I want to do. So that's how. So these are going to be the absolute colors that we can now map onto the 12 notes in the musical alphabet, and hopefully you get an idea of why the analogy works, like where we derived this from. And you might say, hey, look, some of them are pretty close to each other. You might have trouble with like these 3, and that's true. But notice that we're really usually only working with 7-note collections generally. So that means that you might end up, depending on which collection of notes, with these 2 together, but that's just going to be an indication that those are really close to each other. That those would be like a half step away from each other, right? So usually you're going to have at least a whole step away for most of the notes in the 7-note collections when we apply the formula of whole, whole, half, whole, 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 half to it. So now we have colors. These colors are basically as equally spaced as they can be on the color wheel. And notice when we think of it as a wheel, you're starting here if you think about this as a circle, this is about as far away as you can go around the circle. This would be the opposite side of the circle. And then you could see it goes down to here, and they fudged it down here. This is where the magenta fudge factor happens. That's why this color is close to the red, because they fudged it. So the circle goes around. So that's cool. That's good for us because that matches the phenomenon of pitch, which seems to go around in a circle. So that means to get as far away as possible would be going from like red to the middle to like this green, which makes sense because I don't know, like I think in makeup terms, like if you have something red on your face, right? What do people do? They put green on it, right? Because I think it cancels each other. I'm not an expert at this, but I think if you're an actor or something, you've probably, right? Or whatever, like you have red, like, and then you put green on it, right? Isn't that what? I had rosacea before. I think I've tried you put, in my whole face is red, so you just try to put green on it. Then you look green, but I'm not sure if that's an improvement or not. But anyway, but then if you go from here all the way down to here, it's not the full distance away, right? Because even though that's the end of the spectrum happens like here naturally, but then they bent it back around. So that makes sense for us, but the analogy doesn't fit exactly to painting, because if you paint, you would think that you would want colors that are kind of closer together. They blend in together. They're in the same kind of, all the colors within someone's color, thing that they're pulling from. Like if you're doing, Microsoft's color stuff, they're all similar to each other. But when you do the analogy of color onto the sound wheel, it's actually the ones that are more distant that sound more solid. So like the fact that this really loud red, you can almost think of it mapped up against this green, might be something like a perfect fifth, which is right in the middle. It actually calms each other down. It gets you back to, from a Zen standpoint, maybe it gets you back to even. This is too loud and this is too calm. You put them together and they give you a solid sound, a perfect fifth or a perfect fourth. When you get something that's really close to each other, like these two, that would be a one note away minor second. That's very tensiony. It's too close. The fact that you put two things that are too similar to each other together, pitch-wise, is wrong, right? It gives you a bad sound, right? So I don't know what analogy you want to work in your mind to see how the kind of colors work together. So we'll make up a story, right? Stories are good. So here's kind of like what ChatGTP gives me for the color names. So I think, again, it might be good to actually associate these color names. Cyan, I'm not good with color names, so I should get better at that. Violet, and there's magenta and rose. So if we associate these color names with the notes, then we have a permanent, association of color, which again, could only be good to build up the neuron connections. And then what we'll do is we can ask ChatGTP and say, hey, look, this hex numbers are measured based on the HLS in hue, and they are using a lightness, not brightness, they're different, a lightness of 0.5. What's the difference between lightness and brightness? I believe that lightness, the lightness factor will pull you closer to white light, meaning it'll turn all white or just nothing there if you increase the lightness factor, max it out. And the brightness, I know that's the brightness. The brightness goes closer to white light. And then the lightness factor is actually closer to black, right? It's how much, so if you turn the lightness all the way to one direction, you're going to get black. They seem similar. I don't know why they're actually different, but you have lightness or brightness. We're going to use lightness, which is the one that deals with how close to black it is, because I think it gives more contrast. I don't know if it's playing with it. So that means I'm going to say, hey, ChatGTP, take this, which has a maximum of a 0.5 lightness to make it pop as much as possible. And then I think you tone it down. So I went two nods down. So 0.5, 0.3. I think this is 0.3 lightness. And then it gave me the numbers for the same hue, the same length of wavelength, but now it mixed in black. You can think of it, I think, is the proper way to give you a darker. This is what I'm going to overlay on the octaves that are lower in pitch. As pitch gets lower, I'm going to go here. And then if I go up, I said, hey, look, change the lightness from a 0.5 to I think a 0.7, and it gets lighter. So now this can help us to add the next dimension. So remember, we have 12 notes, but we also have octave. So the 12 notes, usually we think of as the middle of the piano, and it should start from A to G sharp, which is 440 to 880, but they actually measure the middle C as the starting point for the middle point, which is kind of stupid. We'll talk about that later. I mean, it's just confusing. Like why? And then they call it C4 instead of like the middle, like 0 or something, because they didn't want, I don't know, we'll talk about that later. But that means that we can map the color directly on that, and I could then look at a fretboard that has all of the A's are red, all of the C's are green. That might be useful for what we're doing, but we could get more complicated and say, hey, look, as we go up to the next set of notes, A through G, which is an octave higher in pitch, I'm going to use the same red hue color, but have the lightness factor toned so that it's a lighter color. Same hue, lighter color. When I go to the left on the piano and I have the same A, same hue, but now a color that's closer to black, a darker color. Same hue, we adjusted a different factor. So I can't measure these colors by adjusting the wavelength. I can't tie then, like if I go an octave up, I can find the actual hertz of the octave up. It's going to be a higher hertz number. I can't tie that higher hertz number to the equivalent number on the wavelength, because the wavelengths, we only have 360. We don't have any higher numbers, but I can say if I'm looking at an equivalent to the hertz, which is an octave higher in pitch, then I'm just going to find the appropriate color and apply the lightness to that higher octave. So it's not a perfect system, but it gives you that higher level, and it allows us to map out the fretboard in a way that might be useful sometimes when you want to work on the different notes that have different pitches, right? I might want to look at all the A's that are going to be an A3, an A4, and an A5 in terms of different octaves. We can do that with adding the dimension of lightness, which we'll talk more about later.